One common way to describe exponential decay is in terms of the half-life. What's the half-life? The half-life of a substance is how long it takes for half of any current quantity to be lost. There are two major places that this description turns up. It turns up in radioactive decay, which is a process in physics where unstable atoms turn into other more stable atoms. It also turns up in medicine to describe the way substances are metabolized. So an example of radioactive decay, we might say that some isotope of carbon has a half-life of 38 years. That means if I have a lump of this isotope of carbon, I go away for 38 years and come back, half of the atoms in this lump of carbon will have turned into something else, either a different isotope of carbon or some other element, depending on the specific decay process. In medicine, we might say that a certain drug has a half-life of 90 minutes. That means if we administer 500 milligrams of the drug now, go away and check back with the patient in 90 minutes, he's only going to have 250 milligrams of the drug left in his system. So how do we use half-life? It's pretty simple. If we're given the half-life, the common ratio is going to be a half, and the scale factor is going to be 1 over the half-life. 1 over the half-life. That seems weird. Let's see an example. Suppose a certain isotope of unobtainium, UU-279, has a half-life of 10 minutes. If we obtain a 500 microgram sample of UU-279, how much remains after 1 hour, that is 60 minutes? Right, so we're talking about a mass. We're interested in the initial mass, the common ratio, the scale factor, the mass after some time, and the amount of time. In this problem, of course, we're given the amount of time, right? 60 minutes. That's easy to spot. And because we're talking about a half-life, the common ratio is surely 1/2. The starting mass is 500, and we're looking for the final mass. What about K? The half-life is 10 minutes. That means how many times are we going to multiply by a half? How many half-lives are going to pass? Well, we're going to divide our 60 by how long it takes the amount to cut in half. Right, we're going to want our K to be 1/10. We're going to want to divide the time by 10. So our equation then, m of t, the thing we're looking for, is 500 times 1/2 to the 1/10 times 60 power. Oh. That's pretty easy to work out, though. Right, we don't need to do any algebra to solve this. Just put this whole thing into our calculator. 500 times 1/2 to the 1/10 times 60. And we could work out these intermediate calculations if we wanted to. That doesn't matter. And we get m of t is 7.8125. Now that's exact. This is a nice fraction. But given what we're doing, we probably want to round. So about 7.8 micrograms remain. Now there's another kind of problem that's very slightly trickier that we might do with half-life. We might also want to find the half-life. So here's an example of that. Another isotope, UU301, is more stable. A 10 microgram sample is obtained, and after 1 hour, 8 micrograms remain. What is the half-life of UU301 in hours? This is tricky, right? We know a starting amount. We started with 10 micrograms, and we know the final amount. It's going to be 8 micrograms. We know how long it took to go from here to here. It took 1 hour. We want to find the half-life. So since we're still interested in the half-life, the common ratio is still a half. The thing we don't know is K. Right? K is 1 over the half-life. Ooh, we've got a variable in a denominator. Hopefully this won't get too complicated. Let's see what happens. Our equation is going to be our m of t equals our starting mass times our common ratio to the power 1 over h times 1. Well, at least we're multiplying by 1. That's going to be easy. So we want to isolate our exponential, divide both sides by 10, and we'll get 0.8 equals a half to the 1 over h. Now we want to rewrite this in terms of the log. So the exponential has base 1 half. We'll have the log base 1 half. The result of the exponential is 0.8. So the argument of the log will be 0.8. And the exponent is 1 over h. Okay, now we want to solve for h. In order to do that, we've got to get h out of the denominator, right? So we're going to multiply both sides by h. Oh, and now remember, this log is just a number. An ugly number, but a number nonetheless. So we can divide both sides by it. Our half-life is going to be 1 over the log base a half of 0.8. So we're going to go to our calculator now, and we'll find the log base a half of 0.8. Or if we don't have that function on our calculator, that'll be the log of 0.8 divided by the log of a half. Okay. And h is 1 over this value. So 1 divided by that decimal, about 3.11 hours gives us the half-life.